In an earlier tutorial, we looked at 4-stroke spark ignition engines and we discussed the 4-stroke spark ignition cycle. In this tutorial, we're going to be looking at compression ignition engines, which are also known as diesel engines, and we're going to look at a number of different things. First of all, we're going to look at the 4-stroke diesel cycle, but in particular, we're going to compare that to the spark ignition cycle that we've already seen previously. We're going to look at pressure volume diagrams for the diesel cycle. And once again, we're going to look at how those compare to the spark ignition cycle, or the Otto cycle. And finally, we're going to look at how we can go about evaluating the efficiency of a diesel cycle. So first of all, it's important to understand how the diesel cycle differs from the spark ignition cycle. Pictured on the screen here, we have a cylinder from a diesel engine, and there's a number of different comparisons when we compare this to the cylinder of a spark ignition engine. This particular diagram has been taken from the Diamond Pistons blog, and I've provided a URL to that website next to the diagram. Now, the first thing that I want to draw your attention to is that in a spark ignition engine we have a spark plug, but in a diesel engine we don't have a spark plug, instead we have a fuel injector. Now, the other important distinction here, as we'll see when we come to look at the cycle, is we draw air into the cylinder. Recall that in the spark ignition cycle, we draw in an air-fuel mixture. So in the diesel cycle, we draw in pure air, and we compress that air to a very high compression ratio, and then we inject the fuel. It's the injecting of the fuel into the highly compressed air that leads to a highly compressed mixture that will eventually ignite. So as the name would suggest, it's the high compression ratios that cause ignition here, rather than the heat or the spark provided by a spark plug. So the diesel cycle is known as compression ignition because ignition takes place due to the very high pressures, whereas if you recall the previous cycle, spark ignition meant that the air-fuel mixture was ignited by the spark provided by the spark plug. And we'll discuss this in a bit more detail when we look at the complete cycle. So moving from left to right, on the left-hand side we have the intake stage. Now once again the crankshaft's going to rotate, which is going to cause the piston to be drawn backwards. There's a number of commonalities with the spark ignition cycle because as that takes place, the intake valve opens whilst the exhaust valve remains closed. The first difference, as we mentioned before, is that it's only air that's drawn into the cylinder. So here we have air rather than an air-fuel mixture. The compression stroke is very similar. The crank continues to rotate, the piston's pushed forwards, the intake and exhaust valves close, and as a result we compress the air. The important thing to note here is that we have very high compression ratios when compared to a spark ignition engine. So the components of a diesel engine have to be very high duty in order to cope with the higher pressures. The next stage is the power stroke. And the big difference here is that we're injecting fuel into the air to produce our air-fuel mixture. Now, as a result of those high compression ratios, the air-fuel mixture actually ignites. So we have compression ignition due to very high compression ratios when the fuel mixes with our compressed air. Ignition takes place and the piston is forced backwards, producing our power stroke. And finally, we have the exhaust stroke, where the piston moves forward in the cylinder. The intake valve is closed and the exhaust valve opens so that the combusted air-fuel mixture can leave the cylinder before the next intake stage of the cycle. Another point that's worth mentioning is that in the spark ignition cycle, the heating phase here during the power stroke we assume takes place at constant volume. And the assumption there is when the spark provides the heat, the air-fuel mixture combusts very quickly. Now in the diesel cycle, what we have is combustion at constant pressure, and we'll see this again when we look at the PV diagrams. So what that means is when combustion is taking place, the piston within the cylinder is already moving backwards. The combustion process takes place over a comparatively longer period of time. So if we have constant pressure in the cylinder, and we have the temperature of the air-fuel mixture increasing, then we must have an increase in volume. The increase in volume takes place at constant pressure. So let's take a look at the PV diagram for this cycle to help to reinforce these points. So in the top right hand corner we have our cycle, and we're going to relate this to the PV diagram for the cycle. When we consider PV diagrams, we actually consider the compression stroke first of all. So positions 1 to 2 in our diesel cycle is reversible adiabatic compression. Now, adiabatic means that this compression takes place very quickly and no heat is lost to the surroundings. That goes hand in hand with reversible, because what that also means is if we was to allow the gas to expand and the pressure to reduce, then the start and end points would be the same. So in theory, we could move from 1 to 2 and 2 to 1 and no energy would be lost because we have a reversible adiabatic process. Now, the next stage is where we differ from the spark ignition cycle. 2 to 3 is constant pressure heating. We note from our PV diagram that the pressure remains constant, so we're moving from left to right with our y-axis as a reference, but we have an increase in volume. As we mentioned before within the cylinder, if the heating takes place at constant pressure and the gas is becoming hotter, then it must expand. And that's why we see 2 to 3 on our PV diagram represented as a horizontal line, constant pressure and an increase in volume. The next stage then, 3 to 4, is reversible adiabatic expansion. So this is really where we're generating power. All the heating's taken place and our gas is continuing to rapidly expand, forcing the piston backwards. Now finally, we have constant volume cooling. And the way that this is represented is that all of the combusted air-fuel mixture is removed from the cylinder and it's replaced with pure air before the next stage of compression can take place. So really 4 to 1 is a combination of the exhaust and the intake phases, as we then return to reversible adiabatic compression to move from 1 to 2. As we mentioned in the previous tutorial for the spark ignition engines, there are a number of different ways of evaluating cycle efficiency for heat engines. The first way is to use something called the Carnot efficiency. Now the Carnot efficiency assumes that we have isothermal processes, and an isothermal process is one where there's no change in temperature. The assumption here is that the heat source gives up heat energy to our air-fuel mixture, but the heat source itself doesn't change temperature. And that's not the best way to represent this type of cycle. It is appropriate for various different refrigeration cycles and so on, but not for this particular cycle. Instead, we can use the ideal diesel efficiency, and this makes the assumptions that we have reversible adiabatic compression and expansion, and it also makes the assumption that we have constant pressure heating and constant volume cooling. So once again, there are some simplifications or assumptions that we have to make when calculating the ideal diesel efficiency. Now, the final way to determine the efficiency of a diesel engine is to use actual efficiency data. Now, in the coming tutorials, we're going to be calculating Carnot efficiencies for diesel engines, and we're going to be calculating ideal diesel efficiencies, but we're also going to be looking at engine performance data to see how we can go about calculating the actual efficiency of various different 2- and 4-stroke diesel engines. So to summarise, in this video we've looked at the 4-stroke diesel cycle and we've made various comparisons to the 4-stroke spark ignition cycle. We've looked at PV diagrams for the diesel cycle, and there we've aimed to emphasise that during the diesel cycle the heating takes place at constant pressure rather than at constant volume. And finally, we've briefly discussed a number of different ways of evaluating diesel cycles.